Thanks. Can you hear me fine? Yeah, okay. Well, thank you, everyone. Thanks, Jules, for the kind introduction. So as the title of my session kind of gives away, I'm going to talk about how switching from sequential to parallel computing can really speed up and increase the computational efficiency of our machine learning models. And machine learning models can get quite heavy, so we might need to distribute them because of two main reasons. One is if we're facing big data, so we are dealing with a lot of data. And the other one, a little more subtle, is if your model is particularly sophisticated, so if there are many parts to your model, that might take long to train. And if you want to have a semi-real time or a quick training, then you might want to distribute your calculations, right? So this is basically what I'll be talking about. So just a few words about myself before we start with the session. I'm Lucrezia Noli. No, it's quite hard for Americans to pronounce it, so I'll be okay with other kinds of pronunciations too. So I am a big data scientist at Dataskills. For them, I'm also the main company advocate all around the world, so going to conferences and giving exciting talks like this one. So I follow predictive analytics projects for the company, which means basically from understanding what kind of data a company has, how they can extract value from these data, all the way to implementing, actually writing the solution and putting it in place, so deploying it within the company's business. Before that, I was working in London for a company that created an AI-based software for retail clients. That was quite exciting too. And I also just became a fellow at Bocconi University. I was happy to know that there's another previous students from Bocconi in the room, so I'm quite excited about that. So yeah, I'm a fellow of the Department of Informatics there. I'm teaching a course on big data analytics. And this is really an honor for me because this is the university that I graduated from not long ago. So it's really exciting to be back there as a lecturer. And besides for the analysis that I do for Dataskills, so for the company that I work for, I guess the biggest contribution that I've given to data science has been my research thesis, which is really dear to me because it's about applying machine learning tools to the healthcare sector. Specifically, I was trying to understand how fast patients with ALS diseases were getting worse. This is a fatal disease, so it was quite a big deal. It was quite impactful for me also to go through all the data. And this research had a quite good feedback, I'd say, because it won the second prize of the PRISLA contest. This is a contest that is run every year to advance research on the ALS disease, which at the moment has no cure, so it's a fatal disease. Okay, of course, if you want to know more about me, you can go on LinkedIn, you can go on the company's page. And if you want to be social and post things on social media during the session, you can use the hashtags that you see here. They're huge at the bottom of the slide. So today, I want to drive home three main concepts. So first of all, I'm going to be talking about the engine that we created. This engine is based on proprietary algorithms, but still I'm going to explain the functioning of it because it's quite sophisticated. It's a sophisticated model. Second of all, I want to focus on the fact that many times the predictions of the model of the machine learning model that you build are not the end of a machine learning project per se, in the sense that these predictions might be fed into the company's business, so your client's business or your own company. So once you have the predictions from the model, as in this case, these predictions have to be fed back into the tool that our client was offering their clients, okay? So the prediction is not the end of your work, basically. And third of all, we used, as I said at the beginning, the capabilities of Apache Spark, specifically in the Databricks environment, but we have done it in a quite different way from other projects that I've seen. So I guess it's going to be pretty interesting to see how we did this, how we used Apache Spark in our project. Before I start with the content of the session, I want to spend a couple of minutes on Dataskills, the company that I work for. And the reason why I want to do that is because most of the sessions that I have attended, that you have attended in these days, were all held by big companies. which is great. I was really excited. But let's say it's more likely that big companies have big data and might want to parallelize and distribute their calculations, right? Whereas for smaller companies like mine, you might think, okay, we don't even need to distribute, like we're not dealing with so much data, or just why should we use such a technology? So I guess it's interesting to understand how we made and we continue using this technology in our day-to-day projects with clients. So the company is called Dataskills, and we are specialized in building solutions in data science. And data science is a really general term that most of the times is used interchangeably with other terms. There's quite a confusion around. So the way that I think about data science is by unpackaging the term into the four main areas of data science that to me are business intelligence. And business intelligence is really important because whenever clients have data coming from different sources, they have to actually make sense of these data and unify them into a unified place. In this case, it's a data warehouse. And there are a lot of other pieces in the business intelligence architecture, but this is pretty much what BI means. And this was the initial core business of the company. Then once you have your data in the data warehouse, you want to do most of the times advanced analysis on this data. So you actually want to be learning from the data and extracting information that is gonna create value for either your company or your client. And value from these kinds of analysis can be expressed both in terms of cost cutting or value creation, or both in the best of the cases. When you're dealing with big data, you both want a BI architecture, and you also might want to do advanced analysis on big data. But of course, because of the features of big data, then you will be using hardware and software tools which are a little different from the ones that you use for traditional data. And then IoT analytics is the latest area in which we are entering. And when you talk about IoT data, is most of the times big data. And so IoT is strictly related to the other three areas. Okay, this is the big picture. So Dataskills is a young company, as I said. If you go on the website, you'll see that we've been around just for a few years. But the people working in the company have actually been in the data science market for many, many years, like about 25 years. And the founder, his name is Alessandro Rezzani. He was actually one of the first people in Italy doing research in business intelligence, like in the whole country. So he did write 3 books that are still now, after a few years, the main source of knowledge written in Italian in our universities and all courses in data science. So I think this is quite exciting. I mean, I wish it's gonna be me in a few years. So we do have a lot of active clients, and the reason for that is because probably you've experienced it as well. When a client starts and puts a BI architecture in place, and he's happy with having all this data coming from different sources well cleaned into a data warehouse, then they want to do more on this data. They want to do advanced analysis. So after the BI project, they might be asking for a predictive analytics project. And starting from the same database, you can actually do a bunch of different analysis of that data. So you might be starting with clustering, but then you might want to do classification, regression, still starting from those same data. So these are projects that can be short, but you can always add little pieces to them. And we do work with fairly big companies too, so you might be recognizing some of the names here on my slide. Lastly, we do have a strong bond with Bocconi University that I've mentioned before. This is an economics university. It's really highly ranked in Europe, but I guess also in the States, so you might have heard of it. And so we do have 3 professors. Well, I'm one of them, so I'm a fellow. I'm not really a full-time professor. But we do have other 2 people in our team that are professors at Bocconi. And we also do a lot of research with the university. The company that asked us to build this engine is called MC Advisory. This is a consultancy company. It's a financial consultancy company. And the peculiarity of this company is that it's really data-driven in the sense that all the services that they offer are based on the analysis of the data. They don't have any kind of relationships with other financial institutions or banks, so they're not constrained to picking just some funds instead of others, which might happen. I mean, actually, it does happen most of the times. So, and this is why I liked working with them. And the reason why they asked us to help them is that they wanted to build a tool which they call the Optimal Portfolio Builder. And this is a tool that they offer to professional investors. So it's a tool for people who already understand a lot about the financial markets, how funds behave, et cetera. And the reason for giving them this tool is because they wanted it to make a lot easier for these guys, so for the professional investors, to pick the best mix and match of funds, so create the optimal portfolio of funds to be offered to their end clients, okay? So we created the engine that is at the basis of this optimal portfolio builder. And the company, MC Advisory, was facing three main problems. First of all, they had all of these data, all of these time series data that depict the fund's yields. And so they wanted to know what to do with them, like how to deal with all these data that were coming in every day. Second of all, they wanted a tool that would be updated every day. So if something changes in the market, if the expectations for a single fund change, they wanted it to be immediately recognized by the tool. So they wanted a tool that if something changes, the predictions that the professional investor is given today are different from the ones he will receive tomorrow, if in the meantime something has changed, okay? And third of all, as I mentioned, so the end goal, that what we will be offering the client is a bundle of funds. So even though, as we will see, we'll go through the whole engine that uses different machine learning algorithms, we have different target variables, we have to prepare all of these time series, but what the client, the end client, will see at the end is just a bundle of funds, okay? So quite a sophisticated project. And this is a visual summarization of the architecture. So we have funds coming in. These are time series of funds yields, I repeat. And so all of these series are fed into the engine. And the engine uses actually a number of different algorithms that predict the fund's behavior. Then there is a scoring method that decides which predictions to trust out of all these models that we've been implementing and training on the funds. And then, as I said, the end goal is to put these predictions within the tool, and then out of the tool comes a bundle of funds. And this whole process has to be done every day. In terms of numbers, we started off with 25,000 time series. And because the aim was to understand the behavior of these time series, we decided that we would actually use 5 different target variables for each of these time series. So in order to depict actually the overall behavior of that fund. And so the 5 target variables are the performance, that is the incremental change in the fund's return. Then there's the value at risk, which is the maximum expected loss. The expected volatility, which in this case is depicted by the standard deviation of the fund's yield. Then there's the peak to through rate that if you know, like if you have in your mind how a time series looks like, that would be the greatest difference between the highest height and the lowest low of the series. And then there's also a proprietary formula that was given to us by the client, which is called the efficiency indicator, that kind of puts together various things. So for each of these 25,000 initial time series, we would have these 5 targets for each of them. And because the model is quite sophisticated, we decided we wouldn't be trusting just a single algorithm. And this is often the case. I mean, we've been listening to this concept for the whole 2 or 3 days of conference, right? You never trust a single algorithm because you never know at the beginning which algorithm will be the best for your problem. So in this case, we compare 6 different models, 6 different algorithms, but we do it every day. Because again, it might be that if some characteristics of the fund change, then the same model that was the best performing today might not be the same tomorrow. Like it might not still be the best performing. So you always want, or we always wanted to evaluate all of these models against the time series. And then the scoring method is because, of course, in the end, you have to pick just one prediction for each of the series for the 5 targets. So you need something that decides which model is the best one for that single time series. And then in the end, indeed, as I said, the output of the tool is a bundle of funds. And I want to start by having a look at how a time series looks like, because this is a kind of data that is quite different from other data that we might be working with for classification or regression problems. So what we are used to see is predictor variables, so the x's, and these are the features that describe the database that we're working with. So for example, if we are working with a database of people, then our features might be their gender, where they live, where they're from, if they're married or not, etc. So these are different characteristics of the database that you use to predict your target variable, which is the y. In time series, this is not the case, because the predictor variables are actually the same feature that you want to predict, but just depicted at past periods of time. So for example, if your target variable is a quantity, and you want to understand how much the quantity of something will be tomorrow, then your predicting variables will be that same quantity today, yesterday, 2 days ago, okay? So this is quite important, because it means the structure with which the data is giving to us is not the structure that the time series models want. So we have to, first of all, we have to pivot the data, and we have to do quite a lot of data processing to put the data in the form that these kind of models want. This also means that when we do the training and testing split to train our models on the training set and then test how well they're performing on the test set, we cannot do it randomly, which is how we would do with other kinds of problems. So we cannot just randomly pick the data points to create the training set and then use the rest to test. Because here the time dependency might exist, so the quantity strongly depend on the quantity a few days ago. And so you have to be time conscious. Your data has to be put like time ordered. So you will use lags from the past to predict lags in the future. Okay, and this is very important for a time series analysis. So how did we start approaching this problem and building this quite sophisticated solution? So we started writing our own algorithms in Python, as we usually do. And we soon noticed, though, that we couldn't have realized the project that we had in mind initially in a sequential fashion, because it would have just taken too long. Because one of the requirements of the client was to have an updated tool every day. And as I'll show you at the end of the performance comparison, this would have taken like a few days to train the whole thing in a sequential fashion. And so if we really wanted to do it in a sequential way, we would have had to decide, for example, cut down the number of target variables, maybe just use the performance and then the value at risk or something. But then that would prevent us from really giving an overall picture of the behavior of the fund. So we didn't want to do that. On the other hand, what we might end up doing would be just to pick a single model that is the best performing and use that model for a few days. So for example, run the whole thing, the whole infrastructure that I showed you before, run it once a week, then you see for each fund which model is the best performing, and you trust that prediction for the whole week. But this might not be optimal, because as I said before, if something in the characteristics of the fund change, or the behavior changes, that model that you've identified a week ago might not be the most performing one anymore. So sequential computation just didn't make sense for us for what we wanted to create. And so we decided to switch to parallel computing. And actually, there are libraries in Python that permit you to do that, so that you can parallelize your code. And one of these is the multiprocessing library. And it does the work. I mean, it does partition and parallelize your code. But the problem with that is still that if you're working on a single machine, then you're limited to the number of cores. So you can just have as many threads as the cores are. You know, like you cannot escape that. Of course, you can start adding more machines, but that would mean that you have to manually distribute your code across all the machines that you want to add. And it's crazy to do because there's someone else who already did it, which is the Spark technology. So we decided to use Apache Spark because of this, because it just wouldn't make sense to start distributing our code by hand if there was already a way to do it without having to code everything. And specifically, we decided to use the cloud because it's really flexible. It gave us the flexibility. Also, we can add nodes really easily, and you can you can decide automatically how many cores to use depending on how much data you have to process, so that's really handy as well. And specifically, we used Databricks as an environment because the user interface is just so easy to use for us. It's really, really easy. Even people who are not really familiar with the technology kind of understand in a 10-minute session how the infrastructure works. And that's great from our standpoint. And we used it on Azure because, well, we are really, we know how to use the Microsoft technology. We are gold partners, so we already used Azure for a bunch of other things. So Azure Databricks was the best choice for us in this case. So how do we actually leverage Spark's capabilities? We use Spark for two different reasons. So one is the data preparation. As I showed you before, the time series data don't come in the same way that they have to look when we feed them into the time series models. So there's a lot of data preparation that we have to do. And the other reason is for model implementation, which is a little more complicated, and I'll go through this. So data preparation, of course, we use Spark SQL as long as we can, because it's just like you have so many functions natively implemented, it works really well. But there's a problem there. We encountered a problem that there were some things that we wanted to do, so some functions that don't natively exist in Spark SQL. So for example, for a time series, the fast Fourier transformation is one of the things that we wanted to do, where you basically unpackage your series, and that's helpful for a number of reasons. It lets you understand better the series. It might add information, and so it might actually increase the predictive performances of your model. And that just doesn't exist natively in Spark. So we still were facing parts of the code that we didn't really know how to translate in native Spark. For what concerns the model implementation, here, as I said at the beginning, we've used Spark in a quite unusual way. And what I mean by this is that usually what you do is you have a single model and you have huge data, and then you distribute that single model. In our case, we don't have, like our data per se, the one series per se is not that big because we only have 250 data points per year, because those are the days in which stock markets are open, and we have a few years. So actually, a single series is not that long. But we do have 6 models, and we do have 5 target variables for each of the time series. So if you do the multiplication, we started off with 25,000 time series. We have 5 target variables for each, and we have 6 models to be run against them. So we started off, and this was just the initial point, with 750,000 time series to be processed every day. Okay? So I say it again, because I think it's the peculiarity of the use of Spark is in this thing. We don't have a single model to be distributed on huge data, but we have a lot of models to be distributed. So we actually want to distribute each of the 6 models to be run and confronted at the same time. Yeah, and then the other thing with the modeling part and the use of Spark is that we haven't actually used MLlib. Partially because of this, because we weren't distributing a single model, but rather we had 6 different models. And then also because, as I said, even though I showed you the names of, the general names of the class of algorithms, these are actually proprietary algorithms. So it's handmade code. We wanted to be using our own functions, so we weren't using any of the already implemented machine libraries in Spark. Okay, so this is pretty much the picture that we were facing. So here there's to the fact that we want to use all of these functions that we have written that basically are working in the pandas environment, not on Spark's data frames. So how do you deal with that? Well, you can use the toPandas function, right? That turns Spark's data frame into a pandas data frame. But if you do that, you are working on the driver node. So you're giving up all the parallelization and distribution capabilities of Spark. And this makes just no sense, because the reason why we used Spark in the first place is that we wanted to distribute both the data processing part and the modeling part. So if at some point at the beginning, even before we do any of the, or part of the data processing, and even before we do the modeling, we go back to the driver node, then just like we're not exploiting Spark at all, okay? So we needed to find a way to work with Spark, write our own formulas without giving up Spark's capabilities. So we came up with a few functions. It's just a few lines of code that we have handwritten, and we've called them in a really creative way, RDD to pandas and pandas to RDD. So this is actually, I think it's a quite smart way to work around the problem. Because what you do is, if starting from a Spark's data frame, you go down one level to the first level of abstraction of Spark, which is the RDD, then you can apply your custom functions and you'll be working in the worker nodes, not in the driver node, okay? So that means that if you go from a Spark's data frame to an RDD, and so you pass through the RDD before you go to a pandas data frame, then you are working in your parallelized fashion. And it's still pandas working, doing the calculations and not Spark, but at least you're not giving up the parallelization and distribution because you are within the worker nodes, okay? And this is quite important. So the steps would be, you take the Spark's data frame, you have to repartition it by series ID because you want a single series to be within a single partition. You do not use the toPandas, but instead you turn that partition into an RDD. Then from the RDD, you go to a pandas data frame, you apply your custom code, and then you do the same process all the way back. So these are practically the steps. You repartition the Spark's data frame, you go to an RDD, then from the RDD to pandas. So the important thing is that you went down a level to the RDD before you went to pandas. Then you apply your custom functions, and here we have a set of functions for the data processing and a set of functions for the modeling. And then you go back to your Spark's data frame. So this was great. I mean, we were quite excited that we came up with some proprietary code to do this, until we figured out that actually someone else has done it, and the other way to do it is by using the vectorized user-defined functions. But it kind of happened at the same time, so we didn't know what they were doing. But it's still great, because the two things actually do the same thing. So pandas UDFs were introduced in Spark 2.3, then developed further in 2.4. And we use the grouped maps that work with the split, apply, and combine kind of interface or way to operate. And basically, so they do exactly what I said. You can apply your custom functions working on pandas data frame, but just using this native way to do it, which is, of course, more efficient because it's natively implemented and existing in Spark. So again, when do we use the pandas UDFs? Whenever we cannot use Spark SQL on one hand for the data preparation and for all the modeling, because as I said, we have some pretty peculiar and ad hoc models that we want to create with our custom functions. So this is an example of the code. I guess the screens are quite big, but yeah, I should be able to see it. So of course, this is not the real code that we've used. I just wanted to show it to you here because you can see all the steps that, that you need to take if you want to use the grouped maps pandas UDFs. So first of all, you need to define your output schema. So you need to define how the output data will look like. Second of all, you have to group by. In this case, we group by the series ID, as I said. And in the definition of the function, if you notice, if you read the code, there's another group by. And some of you might think, OK, this is not necessary because I've already grouped. And it's true that the second group by within the definition of the function is not necessary. This is a tweak, it's kind of a trick that we've used so that we could apply any functions that we wanted. So in this case, we're just creating something quite basic. It's a rolling window with 200 data points. But when we did not use that group by within the definition of the function, the code didn't work. Because of the structure, like because of how it's made, it requires a group by. So this double group by, if you go through the slides again, that's why. It's because it was the only way for us to actually use whatever functions we wanted, as in this case. So for the data modeling works in the same way. I haven't put the schema here, but you will need to define a schema as well. Here I wanted to underline the @pandas UDF, and this is called the decorator, which is basically something that supercharges whatever function you put there. So it gives it additional functionalities. For example, the fact that you can go from a Spark data frame to a pandas data frame and vice versa. So this is what you use, this decorator. And then, of course, within that, when you define your function, over there you can write whatever you want. Any kind of ad hoc code you might have developed. So this is what we used actually in production. It was kind of a waste of time to create the RDD to pandas, but not really, because still, I mean, we came up with something that the other guys were working on as well, so it's quite great. And so this is the performance comparison. If you see, well, I split it for the two main uses that we make of pandas, or for the two big necessities that we have for distribution in our model. So on one hand, data preparation, on the other hand, the modeling part. And data preparation takes about 4 seconds per series. So already, if you do the calculations in a sequential fashion, it takes 28 hours just to do the data prep. Now, of course, this doesn't make any sense. The machine that we've used has 10 worker nodes and 32 cores, so it has 320 processors. So when we implemented our own code with the RDD to pandas and pandas to RDD functions, the whole process took about 1.5 times more than with the pandas UDFs. Which, I mean, it's not that bad considering that the pandas UDFs are native into Spark and our system is not. So if we were to deal with the less data or with the little less complicated framework, it might make sense to be using it because it works just fine. I mean, it's not that bad. It would still take like less than 3 hours to do the whole computation. So, I mean, it is quite good. It's quite impressive. But if you have really complicated models, and this model is about to get a lot more complex for us, so in this case, it still makes sense to use the pandas UDFs. Okay, so that is the best choice for us. It takes less than 2 hours, 1 hour and 44 minutes to do the whole thing that I've showed you at the beginning. So it's quite complicated, quite impressive. So this is an ongoing project. I don't know if I've mentioned it at the beginning, but even if it started with this one company, so working with time series depicting funds yields, we are actually going to present it to the market as a product because it's quite easy to generalize it and so to use this engine for different kinds of time series data because time series might be funds, might be stocks, but might also be things completely different and unrelated to the financial market at all. So this is quite cool. Within this project, we are expecting growing complexity in terms of more funds that we will be analyzing. If we have more funds, it might be that the new funds behave in a different way from the ones that we've been analyzing so far. So we might be wanting to add additional target variables just to have an even better idea of how the funds behave. And also, we might be adding other models because now we've seen, I mean, it's still really fast. So as long as we find models that behave well, it makes sense to add them. It's not that complicated. Another interesting thing that we can do is an analysis of differentials, which means instead of comparing fund by fund, as we do now, you can also compare, on top of that, each fund to the average of the market that that fund is into. So this adds additional information to your model. And another interesting thing that you can do is the time series clustering. So you can try and understand if there are funds that behave similarly, and so that you can put them in the same cluster. And why would you need this information? Well, because you can use it in data processing. So if you have missing values, instead of imputing using the average or whichever other metrics from the overall set of funds, that you would be picking that value to impute just from the cluster of that fund, which should give you a much better estimation of the value that you are imputing. On the other hand, also, this is an information that you can add to your model, information about which cluster the fund belongs to. Finally, there are also better ways we think that we can make use of Spark. So for example, if we can understand and identify exactly how long each of our processes take, we can avoid to have worker nodes that have to wait for other nodes to be finished. Okay, so we can kind of balance the computational time that different parts of the model take. Also, I was excited to hear the news about Spark 3 yesterday at the keynotes. So actually, there will be generalized user-defined functions that might help us and might speed up the whole infrastructure. And also something that another friend of mine has been working on, and it's really cool. I didn't know about it till yesterday, which is koalas. And so that might mean that we won't be using user-defined functions at all. We can just use our pandas code. But we will see. So this is all really exciting. It's an ongoing project. Already we had many things in place. And yeah, we'll keep on being excited about it and using Databricks Spark for this. OK, thank you, guys, for your time.
We've got about 3 minutes. There's a mic here in the front. If you want to ask any questions, please queue up.
Hi, thank you for the presentation. I have one question regarding something you briefly touched upon in the beginning.
Yeah.
So the goal of the system is to offer a recommendation to customers for which funds to purchase.
Sorry?
The goal of the system is to offer recommendations for specific customers, right?
Yeah. So the tool is for professional investors that can basically they will put in the tool characteristics about the end client, so their level of risk, for how long they want to invest, the risk profile, like these general things. And then, but these are external filters that don't impact the model. It's just a way of filtering, like once the predictions are made, and then you have an idea of how the funds behave, then you filter out with the external information that you get about the client, and then you create your bundle of funds.
Okay, so my question is, do you do any estimations, prediction of the beta of each fund, the correlation with the market, and if that is...
That would be the analysis of differentials that I mentioned. So it's something that we've been thinking about. We are not doing it at the moment, but it's one of the things that we might be implementing next.
So you don't have yet computation speed gain available because you haven't implemented that yet in Spark?
No. So the initial model is already implemented.
No.
The thing that you asked about, so the correlation with the rest of the market, not yet.
Okay.
It's one of the things that we will be working on in the future.
Yeah. Thank you.
Okay, we have time only for one question. But Lucrecia will be
I'll
around.
be here.
She'll be outside. She can answer questions. We have to prepare for the second speaker. So go ahead and make it short.
Okay, so we are kind of...
Can you speak in the mic so we can record it?
Hey, can you guys hear me? Okay. So we are kind of working on a similar problem, what you talked about, kind of having parallel executions within the same Spark context. If you have some comments on cases where we have like a skewness in the data where we partition by, so let's say we have 50 jobs and some of the jobs are much more computationally extensive than some of the other ones, which means certain worker nodes and vectorized UDF would ultimately kind of finish a lot earlier than the other ones. So did you kind of run into such cases? And how did you kind of went through it?
So hopefully there weren't huge differences, but we do have, like, out of the 6 models that we run, there are some ones that are slower than others. So for example, the LSTM-like model, it's quite complicated. It's the one that takes the most time. So it doesn't actually take those 15 seconds. That number that I gave you, that's an average of how long these 6 take. So yes, we do have the same problem that some of the models are slower than others, but it's not that huge at this point. Of course, if it will get worse, so if we will have even more difference in times it takes, it is something that we have to address. So it is part of the smarter way of using Spark that I've mentioned in my last slide. So yes.
Give a big hand to Lacracia. Thank you very much.